So how are you guys doing? I'm going to go over a scene from the Spider-Man No Way Home trailer. I don't normally do this as a video. I would write it out. I've done a lot of these analysis of things that happen in these shows, but I'm just going to try something new, do it as a video, post it on YouTube, see what happens, see if you guys like it. If you do, I'll do more. You just let me know. Okay, so let me just play this part of the trailer. Maybe this is a spoiler. I don't really know. It's trailers, so I think it's fair game. I'm not going to really do that. But so this is part of the trailer. Let's see. Okay, so in this, something's happening. There's Spider-Man. There's MJ. Spider-Man falls off. No, MJ falls off. Spider-Man jumps down to go get her, and then we don't see what happens. Of course, it's trailers, so they don't want to show you what happens. But and this is a classic from the comic books. If you go back and I think it was in the early 80s, Spider-Man's girlfriend, which was Gwen at the time, fell off the building. Green Goblin, I think Green Goblin pushed her off, and he did grab her, but then in stopping her, she died because she stopped too fast. So I don't know what's going to happen here. Super pumped up about Spider-Man, so let's just look at this thing. Now, one of the things you'll notice in this clip is that it's not in real time, right? So it's in slow motion to make it more dramatic, and the camera pans. So if I want to use video analysis to get the position of MJ and Spider-Man during this fall, then I'll have to take that into account. Fortunately, you can do that, and I'm going to use tracker video analysis to do that. When I do that, boom, this is what I get. So this is a plot of both MJ and Spider-Man as they're falling. The top one is Spider-Man, the bottom one is MJ. I roughly estimated the scale, the distance scale, using the scaffolding that you see there, and the time scale's wrong. Okay, but if we use the definition of the average velocity, which is the change in position over the change in time in the y direction, okay, since this is plotting y versus time, then the slope of this line would be the velocity. So if I do that for Spider-Man, I get negative 2.57 meters per second. And if I do that for MJ, they look about the same slope, but they're not. Negative 2.42 meters per second. Now, those are fake seconds. Okay, but again, I don't know the time scale. I could probably figure it out, but I didn't bother with that. So let's see. Are we still okay? So if that's the case, first I want to say, is this what we'd expect? And the answer is no. This is not what we'd expect for falling people. And you may say, what about air resistance? I'm going to get to that. Okay, so suppose I have a falling object just like this. There's a downward pulling gravitational force near the surface of the Earth. That force is equal to the mass of the object times g, the gravitational field. If I set that equal to the mass times acceleration, the masses cancel, and I get the acceleration is in the y direction is negative g. Now, for an object with a constant acceleration, this is the position as a function of time equation we should expect. This is one of the kinematic equations. This just says the final y position is equal to the initial y position plus the initial y velocity times time minus this 1/2 gt squared. And that is not a straight line. If I plot y versus t, that's a parabola. It's not a straight line. Just as a reminder, this is the what we're seeing from MJ and Spider-Man. They both have just constant velocities, and that's the equation for constant velocity with a zero acceleration. Okay, so suppose that they are falling with a constant velocity, which is, I don't know, not really what it should be, but that's fine. I'm cool with that. I'm cool. Could and would and when would Spider-Man catch MJ? Okay, so here are the two equations of motion for both Spider-Man and MJ. Now you notice that I'm going to start off Spider-Man at, I just roughly got this from the video, 1.99 meters above him. Now, again, that's just looking at where they start at time t equals 0. Now, if he could get around, I'm going to guess, 0.75 meters away, center to center distance, then he could grab her hand and catch her. Okay, so there is my position of Spider-Man, there's my position of MJ, and I want the distance between those two to be 0.75. So if I just set distance as ym minus ys, I can solve for everything. So d is ys minus ym. So I'm just going to put in the expression for this position of Spider-Man, the position of MJ, and then solve for t. Really, that's all I have to do. So it's d, the distance between them of 0.75 meters, minus the starting position divided by the difference in their velocities. If you plug that in, I get 8.27 seconds, and again, fake seconds, okay, because I don't actually know the time scale, but it doesn't matter. I can take that time, put it back into my equation for MJ, YM, and I get that she falls 20 meters, and then he catches her. Now, I think they're on the Statue of Liberty. I'm not 100% sure, and so that 20 meters is pretty far way to fall, but I think they may have enough distance and to catch her. Okay, and that's from the trailer. So he's definitely going to catch her. He's going faster than she is. He's going to catch her, assuming they keep moving at the same constant velocities. Okay, what about a more realistic catch? And in fact, I should make sure I'm not covering up stuff with my face. I wasn't paying attention. Okay, so people don't fall at constant velocities, they fall with constant accelerations. So here's some assumptions that we can make. Number one, MJ starts to fall and has initial velocity of 0 and a constant acceleration. Spider-Man starts at the same place, but after MJ has already fell 3 meters. And I don't know where I got that 3 meters from. It's really hard to tell, right? Because they switch scenes back and forth. So Spider-Man, I don't think, is actually starting at the same spot. He's starting from somewhere else. But, you can change this problem to make it the way you like it. Now, I'm also going to assume that MJ can fall 20 meters. So Spider-Man has to catch her before she falls 20 meters. And that's going to give him enough time to slow her down and stop with a reasonable acceleration that doesn't cause injury or something worse than injury. The other thing is that, again, Spider-Man has to get 0.75 meters away, and at t equals 0 seconds, Spider-Man starts at y equals 0, and then MJ starts a little bit lower. So that's where I'm going to start my clock, right? My clock starts at t equals 0, and Spider-Man's right there with some non-zero velocity. If he had a 0 velocity, he wouldn't catch her, right? Okay, so in order to do that, if Spider-Man starts off at t equals 0 and MJ starts down here, then I need to know how fast she's going. So this is one of the kinematic equations. If you take the kinematic equation and the definition of acceleration and eliminate time, you can get this. This says the final velocity squared is the initial velocity squared minus 2gd, well, the distance fall that she falls, df. I'm calling that the fall distance. And so I'm assuming she starts at 0 velocity. So now I can just solve for that velocity, and I get the square root of negative g df. And g is a positive number here, but df is not. She's fallen down negative 3 meters. Okay. And if I plug that in, I get negative 7.67 meters per second. So think if you're Spider-Man. She's ahead of you and traveling faster than you, and you need to catch up. And you're going to have the same acceleration as her. Okay, so let's just guess. Let's just guess that Spider-Man has twice that initial speed, and plot the vertical position as a function of time and see what happens, just to give us an idea of what it would look like. So if he starts off and jumps down with this velocity of negative 15.3 meters per second, then he's going to have a parabolic path. She's going to have a parabolic path, but he's going to start with a greater slope. And that point where they cross right over here around 0.4 seconds, that's where he would catch her. And he would actually even be further away than that because he doesn't have to actually get on top of her. And that would be 6.5 meters. So if he started off at that speed, he would catch her. Okay, so 15.3 meters per second. We just guessed, and that would work. But what about the minimum? What's the minimum speed that he would have to go? That he's going to have to jump down. He's jumping down, so he has a velocity that's not 0. And what would that velocity be? Okay, so let's start off with the position function for MJ. She starts, I think I'm switching this back, because she started with a position of 0 and a velocity of 0, then this would be her equation. And we can find out how long it takes her to get down 20 meters. That's what I want to do. How long does it take her to fall 20 meters? I'm just saying she starts there, she falls, and that's how long she has. And so, because Spider-Man has to get that same amount of distance. Okay. So there's y is 20 meters, and I don't even think I need to do it this way, but that's going to take her 2.02 seconds, okay, to fall that whole 20 meter distance. And so if she fell 3 meters, then I need to think about it's easier to think about this in terms of times, right? If Spider-Man waits, if I knew how long he waited, but I don't because it's not in real time, but I can estimate the distance. So if she falls 3 meters, I can find out how long it took her to do that, and that's the time, leftover time, that Spider-Man has to get down to that same bottom, okay? So if she falls 3 meters, that takes 0.78 seconds. So that means the leftover time of 1.24 seconds. That's how much time Spider-Man has to get to the bottom. And now I can just plug that into Spider-Man's kinematic equation, solve for the initial velocity, and I get 10.1 meters per second. Now, is that realistic? Well, of course it's not Spider-Man, but, you know. Is that like crazy bad? So let's just think if he could jump with the velocity of 10.1 meters per second, suppose he jumped up. So he starts with a velocity of 10 meters per second, and he goes up to some height. How high would that be? Well, there's your height. I can again use that same equation. The final velocity, which would be 0 at the highest point, is the initial velocity, which is 10.1. And then I want to solve for the change in height, and I get 5.2 meters. So, I mean, Spider-Man can jump that high. I'm pretty sure Spider-Man can jump that high. So that means that he could jump down that fast too. Okay. So there you go. So what about air resistance? Don't worry about that V, but imagine I have Spider-Man falling down with some constant velocity. Because the question is, maybe there's air resistance, and that's why they're going at constant velocities, they're terminal velocities. So if you have a person jumping out of an airplane in this position, which they're not in that position, they're moving down with some velocity. There's the downward gravitational force, we already saw that. But there's also this upwards pushing air resistance force, and you can feel that if you stick your hand out of a car window, you can feel the air pushing against that. This air resistance force, here's an equation for that. This is a vector equation. I didn't have to put that. But in this equation, rho, the one that looks like a P, that's the density of air. A is the cross-sectional area of the person. C is a drag coefficient. Okay, and then V is the velocity. So it depends on the velocity squared. As you go faster, you have a greater air resistance force. The total force on the person would then be the air plus the weight. And these are vectors. One's not going to be negative. It's fine the way it is. Okay. Now, at terminal velocity, that's when the total force is equal to 0 and they stop. They have 0 acceleration. They move at a constant speed. That happens when, in a scalar version, mg is 1/2 rho ACVT squared. Now, we don't know the area of a person. We don't know the drag coefficient of a person. But one of the things I use is if you're skydiving in this position, your terminal velocity is about 120 miles per hour. That's about 54 meters per second. So if I know that terminal velocity for a skydiver, I can solve for AC for someone that's falling too. And that's important because now what I can do is take a person, I know A times C, I can just calculate the forces and the acceleration and let them fall and see what that motion would look like. And then we can see, is falling 20 meters, is it okay to ignore air resistance? How far do you have to fall to get a terminal velocity? All that stuff. Okay, so here is a Python code, and I'll link a video down below where I show you how to calculate this whole thing. But this shows two plots. The red is falling without air resistance, and the blue is with it. And this is velocity versus position, right? So you'd actually start from the right hand side of the screen. Okay, right over here, and you're moving that way. And so as you fall without air resistance, your velocity just keeps speeding up and up, and you don't get, even after 70 meters of falling time, you're only at 35 meters per second. That's not terminal velocity. Now, it takes longer for the air resistance to get there because as you go faster, that air resistance gets larger and larger, and so you have a smaller and smaller acceleration. And even after falling 60 meters, you're only at 30 meters per second. But the point is, if you look at this minus 20, that's where we were at, falling 20 meters. The difference in the two curves is just not anything, right? It doesn't matter. And it'd be even worse because if they're in this vertical position, they're falling like this, then their cross-sectional area is going to be even smaller. They'd have a higher terminal velocity. Those two things would be just right on top of each other. So you don't have to worry about air resistance in a case like this, falling at this short of a height. But that's my analysis of Spider-Man. Hope he catches her. Really excited to see the movie. And I'll see you there. Actually, I'm not going to see you there. You might be at the same movie theater I'm at, but I doubt it. Okay. Bye. but I'll probably have another analysis before it. Let me know if you like these kind of videos. I have a whole bunch of old stuff that I can turn into videos about science fiction, Star Wars, The Expanse, superheroes, and if you like it, I'll keep doing it. But if you don't like it, I'll probably still keep doing it. But okay, so that's that, and I switched out of something else, but that's fine. I'm out.